So this is an example of how to do a flux integral, just as really just to walk through it. We won't do a lot this way. Let's assume we have a cube of side L, and one corner of it sits on the origin, and the others extend, all the sides extend into the positive quadrants. And we're going to try and integrate the flux due to this electric field, which is entirely arbitrary and a little bit silly, but is easy to do, so that it grows with the position in x or z, but is constant in y, and it always points parallel to the z-axis. And so to illustrate it sort of quickly, we'd have something like when z is 0, it'd be sort of 0 on the back board there, but then increase with x and increase with z. So something like this without any real good scale. All right, and then I'm going to clean that up a bit. For completeness, or at least for clarity, I'm going to label the faces. So the front face is 1, this face is 2, this face is 3, and then the corresponding opposite side is whatever number adds to 7, just like a regular 6-sided die. So the back wall, this wall back here would be 6, and this wall would be 5, and down here this floor would be 4. We're not going to need them that directly, except for, well, we'll see 1 and 6. And so we want to find the flux, which is the closed surface integral of E dot dA, which is going to be the open integrals of over face 1 plus over face 2, and then face 3, and then face 4, and then face 5, and then face 6, all of these integrating E dot dA. This notation is terrible, and a math teacher would probably yell at me for it, but it's fine for us, because what we see is that over face 2, the normal points outward, but the electric field points along the surface, and their dot product, therefore, since they're perpendicular, is 0. And likewise, for face 3, the normal points in the y direction, but the field is in the z direction, and so it's also going to be 0. And then for face 4, it would be pointing, the normal would be pointing down, but the electric field is in the z direction. Those are perpendicular, so that also goes to 0. And then for face 5, the normal points, you should sort of see it, out, but the electric field points along, and so once again that becomes 0. And so our total flux is really going to be the flux through face 1 and the flux through face 6. And that's all we have to worry about, which is nice. So now let's compute the flux through face 1. Okay, so we're looking for the flux through face 1, which would be the integral over face 1 of E dot dA. And there's some good news and some bad news. E varies over the face 1, so we can't just sort of pull anything out of the integral yet, but on the other hand, we have a couple of things that are useful. We can subdivide our face into a lot of little grid marks. This is the standard calculus thing of saying I'm going to take my surface and I'm going to subdivide it so that I can talk about a particular spot. So let's call that one. All right, we're going to focus in on some particular one. Doesn't really matter which, just a representative one. It's going to be that one. And we can see that the position of that is given by, well, certainly x, certainly y, and then its position out from the back, which would be its z-coordinate, is the side of the cube. It's that far along. We can also see that it has a width, which is dx and dy. So the area as a vector, well, its scalar part is just dx times dy, and then the normal from that little bit comes out that way, which we can see is just z hat. So that's our area. And I want to remind you that we already had the electric field, which was given as this, well, again, silly, but for us, functional electric field. It's a really weird electric field, and of course its units are completely wrong. So don't freak out too much about that. There really should be some sort of proportionality constant out here. So I'll put that in, and that would be whatever gets us to newtons per coulomb. And don't worry about it, we'll just take it as a multiplier. So across face 1, dA is the area of that little tiny square, which is dx times dy, and it has a normal, which is z hat. And the electric field is, well, x plus L, and has a direction which is z hat. And I put the L here because we are L away, right? We're a coordinate of this whole plane is a coordinate of z equals L. So I can just plug that in because I'm not integrating over it anyway, so it's not going to change, right? It is a constant for face 1. Now we can find what E dot dA is. So E dot dA is, well, we have x plus L z hat times dx dy times z hat, and of course now this is the dot product between them, but we know that this dot product is just 1. So we really just have x plus L times dx dy. I'm also going to put that we really should have some constant of proportionality because x is not a proper electric field. I need newtons per coulomb, but my field strength was only in meters, so I need a constant convert between them. I'm just going to call that k. I don't really care about it. All right, and then phi 1 is the integral over all of that. So what does it mean to integrate over face 1? Well, it might mean pick some value of x, so go over some value of x, and then integrate that strip. In fact, what we really want to do is integrate that strip, and then that strip, and then that strip, and then that strip, and so on, which means we want to integrate a strip which is from 0 to L of our E dot dA. So k times x plus L dx dy, and then I want to integrate it. Right, that's like that strip, but then I want to make sure that I get all of these. So I integrate again from 0 for x to L. And I guess theoretically I should really be saying, and that's where that dx comes from. So I take everything that isn't y and I play with it as if it were constant. So that gives me the integral, well, let's see, our constant k can float all the way outside. And then I'm kind of stuck because at that point, integral 0 to L for dx, but I can't really do much with this because now I have the integral from 0 to L for y of x plus L dy. But for an integral over y, x and L are both constants, and they can come out front as well. So I have weird constant k times the integral from 0 equals x to L of dx times stuff, and that stuff's going to include an x plus L times the integral from 0 to L for y over dy, which is easy and nice. So I can say, okay, bring the constant out front again, deal with our integral from 0 equals x to L dx x plus L, and then this is just y evaluated from 0 to L, which is just L, and that will come out front as well. So now I have KL out front, and I have the integral 0 for x going up there of dx x plus L. which is the integral of something times a constant, right? Something of x plus a constant. So again, let's bring KL out front. Oops, it's pretty bad writing. And when we do this integral, we're going to get a half x squared plus Lx, all of it evaluated from 0 to L. And then we just keep grinding, and we have KL, and then this becomes 1/2 L squared plus L squared. And so all said and done, we get KL is a 3/2 and a cube. We get 3/2 KL cubed. Now we want to get the phi along section 6, which if I draw it sort of looks like this back wall, and then we would have some other element like this one, and the element for that would be, the normal for that would point in the minus z direction. But we still have that dA here is going to be x plus, going to be dx dy, same magnitude, but in the minus z hat direction. And then we're going to have the electric field, remember, was x plus z, still in the z hat direction. That lets us say that E dot dA is x plus z times dx times dy times a minus sign that we can bring out front, and then z hat dot z hat, which is 1. And so the whole thing ends up being just minus x plus z dx dy. And for consistency, I really should have that weird constant out front, so we'll put that in everywhere. So our flux across face 6 is the integral from 0 equals x to L of 0 equals y to L. And then I can say times minus the constant. And I can really just say times x because z is 0. And then dx dy. So we bring the minus and the constant all the way out front. And we go from x. And then we'll integrate again over y first. It doesn't really matter which. And our function will be x dx dy, and we can bring everything that isn't a y out front, which is, everything. So we have minus k, integral from 0 to L over the variable x dx times the integral from 0 to L of dy, which is pretty easy. So we end up with minus k integral from 0 to L on the variable x of x dx times y evaluated from 0 to L, which is minus k integral from here of x dx times L, or minus kl integral from 0 to L of x dx, which is minus kl times 1/2 x squared evaluated from 0 to L, which is minus 1/2 kl cubed. So that's phi 6. Then we can just say that the actual flux is phi 1 plus phi 6, or 3/2 kl cubed plus minus 1/2 kl cubed, or just kl cubed. So that's our total flux through this total cube. And that's quote-unquote it.